on statistical mechanics. This course is designed particularly for undergrads who are pursuing their bachelor's in physics, master's students as well as in PhD students, and is designed for physics major students. Now, the structure of the course is the following: that first we are going to review thermodynamics, and then we are going to move over to statistical mechanics. But in between these two, we are going to review very briefly probability theory. Now, thermodynamics, why thermodynamics? That's a very natural question. Now, thermodynamics deals with behavior of systems as a collective body. In some sense, it's unique as compared to your classical mechanics and quantum mechanics. It does not give you a new equation it doesn't develop anything new, such as a Newton's equation of motion or Schrodinger equation of motion, but rather it uses some of the old tools, some of the tools that is already existing to study such systems. Now, for example, take the system of a liquid which is contained within a container. I'm sure you have the first things that comes to mind, that if you are given a bottle of a clear liquid, if I ask you what kind of questions can you ask, then the first thing that you ask is what is that liquid, which means what is the chemical composition of that. Well, and then the questions that arises in the mind: at what is the temperature of the liquid, what is the pressure of the liquid, what is the density of the liquid. Now, these are very general questions, and these questions are essentially within the scope of thermodynamics. Answering these questions are within the scope of thermodynamics. So, if I take, for example, a container of liquid, so the typical questions that you can ask, of course, is chemical composition, the temperature, volume, density, pressure. All these are valid questions that you can ask. But you see, nowhere you ask what is the interaction between the constituent particles of the liquid. So in some sense, this is never asked in thermodynamics. You never ask the microscopic interaction between the particles. So the need for thermodynamics arises from the fact that classical mechanics, as we know it today, has its own limitations. What does it mean? It means that if I give you one single particle, and if you know the force on that particle, then you can very clearly find out the trajectory of the particle given the initial conditions. If you do not know the initial conditions, then of course you have a family of trajectories. If I give you two particles, which you have already done, you can go to the center of mass frame and analyze their motion exactly, analytically. Three particles, it is still doable. More particles, if you keep on adding more and more particles, then the problem no longer remains analytically tractable. You have to resort to some kind of a numerical scheme. And with the advancement of computational resources, at best we can go to 10 to the power 6 particles. At best we can go to 10 to the power 6 particles. But that also, simulating such a system is also very, very time consuming. In contrast, if you look in nature, then you know that a typical Avogadro number is 10 to the power 23. So it is just not possible to analytically track such systems as well as to track it computationally. So what do? We have too much information in our hand and we just do not want to deal with so much information. So we sacrifice some of the things. And the whole idea in this respect is to rather not to go into microscopic details, but to look at the system as a whole. And for that, you see, a thermodynamic system is always characterized by a set of variables which are macroscopic in nature. So a thermodynamic system is always characterized by macroscopic variables. And we just saw what these variables are for a hydrostatic system. A hydrostatic system is a system which is typically a fluid or a gas. I mean, the general term is the fluid. It's either a liquid or a gas. A hydrostatic system such as pressure, volume, particle number, temperature, so on and so forth. I mean, it can be a different system, but we always describe it with a set of macroscopic variables. We shall call this, let's not introduce the notation right now. So there's a set of macroscopic variables. What are these characteristics of this macroscopic variable? Please remember one thing, that any system that you consider, if this is your system, I have two perspectives of looking at it. One is the macroscopic perspective, which we just described. The other is the microscopic perspective. A macroscopic perspective, as we just defined, is essentially looking at the system as a whole, but not zooming into the system. Now, all these macroscopic variables that we have written down over here has a very interesting characteristic in the sense that there are no fluctuations in the system, in these parameters, or in these variables. This is not really true, but thermodynamics chooses to ignore these fluctuations, and therefore the kind of questions and answers you can get from thermodynamics is also limited. We'll get there in time. So there are no fluctuations in these variables. Clearly, if I, for example, measure temperature as a function of time, then thermodynamics tells me that this temperature is a constant number. There are no fluctuations. In reality, of course, if you measure, there is going to be fluctuation about this average. And this average temperature is the one which describes this system within thermodynamics. It's also true for pressure, right? And if it's an open system, which means it can exchange particles with the environment, then of course your particle number will also vary. But we will come back to the essence of this. But in reality, this doesn't happen. In reality, for example, if your system consists of n particles which are moving around, so if I have a container which has gas particles, then I know that these gas particles are all moving around randomly, right? This is what you have learned in your kinetic theory. So clearly, this picture is different than this picture. In this picture, you can easily see that I am looking into a more microscopic. I'm looking at the system more microscopically. What does that mean? That if I want to measure temperature at this instant, and if I want to measure at this instant, so if you have a thermometer, let's say if I attach a thermometer to this system, and if I want to measure the temperature of this system, then clearly that measurement equipment also has a certain time scale. But within that time scale, I can see that this particle probably has moved to over here, this particle has moved to over here, this one has moved over here, this one has moved over here, so on and so forth. So there is a rearrangement of this particle position within the time scale of my measurement. But yet, these thermodynamic variables do not change with time. So this is a very, very crucial thing for a macroscopic variable, that they do not change with time. In contrast, microscopic variables, if I really look into the system, the microscopic variables are fluctuating, which you can obviously see and which you can intuitively understand that if I want to try to measure something, then it is very clear that within the measurement, my particle positions have changed. So, alright. So, here if I want to measure the here I have shown you for the temperature, I can do it also for the pressure. But if I want to take two pressure measurements within which will have a certain time lag between these two, then it is clear that within that time this microscopic these positions of the particles have changed. So you see, this is within the purview of statistical mechanics. Here, if you want to know the position of the particles, then of course you have to know the interparticle interaction. Thermodynamics does not care about that, right? So this is one of the very interesting characteristics of thermodynamics, that it describes the system within using a set of variables which we shall call microscopic variables and or thermodynamic variables, which has no time variation, right? So let's remove all of this from this. Now let's take a specific example where I want to talk about well, we just saw one of the system that we considered was gas particles, and here I can see that within my measurement window, time window, the microscopic variables have not changed. So when you then the question comes in, if I want to look at a system microscopically, for a system with a macroscopic picture, the thermodynamic variables in the macroscopic picture, the thermodynamic variables describes the state of the system. This is very important. It describes the state of the system. So if for this particular system of gas particles, n gas particles, which is contained within a container, if I want to change the temperature, then it goes to a new thermodynamic state. If I change the pressure, it goes to a new thermodynamic state. So for a gas particles, or we shall write generally as a hydrostatic system, where it is described by P, V, N, T, U. Looking at this, and for a hydrostatic system, I do not, okay, right now let's just write it down in the following way, that I have these thermodynamic variables, and the state of the system is clearly defined. The thermodynamic state of the system is very clearly defined by this thermodynamic variables, by these macroscopic variables. So if you change any of these, for example, if you change the pressure, if you change the temperature, if you change particle number, which means you also change the density, then it goes to a different thermodynamic state. What about the microscopic picture? But okay, so this is what is called a macro state of the system. What about the microscopic picture? Now the microscopic picture, I know here, but for this particular system, that all of this given macro state, for a given macro state, which means that for a given value of pressure, volume, particle number and temperature, there corresponds to an infinite number of microstates. Why? Because I know that if the pressure of the thermodynamic pressure of the system is fixed, even though it is fixed, the particles within the system constantly undergo motion, right? So they change their position and momentum. Therefore, a microstate of this system is characterized by the position and the momenta for a hydrostatic system. Remember this, we are going to use this later on. There are 6n momenta and coordinates. Now you know that such a space which is made by the position and the momenta is what is called a phase space. You have studied this in your classical mechanics. In the phase space, if I have the possibility. So this is a 16-dimensional space, but if I can visualize it or something, at any instant of time, your macro state is fixed. You have not changed any of these variables, but your microstates, which is comprised of the position of the momenta, form a point in your phase space. So if this is your phase space, then this is a point in the phase space. Clearly, if you can devise a way to measure the microscopic position and the coordinates of all the particles, then you see you can track this. This corresponds to a line or a trajectory in the phase space. Let's not call it a line, a trajectory in the phase space. All of these points which lie on this trajectory corresponds to the same macro state which you have prescribed. You have not changed the macro state. Therefore, for a given macro state, it is always that it corresponds to an infinite number of microstates. Now, this is a particular example where your degree of freedom can take continuous values, or your microstates can take continuous values, because Ri and Pi can take continuous values on the real line. We can even consider a discrete system. And if for this I will take, let's say, not n spins but 3 spins which are magnetic in nature. Now I am asked, so what are the, and they can be in a up or down state. If this is the case, then what are the possible configurations I can have? I can have up, all the spins up. I can have all the spins down. I can have 2 spins up, and there should be one more, which is this, and I can have 2 spins down. Since each of these can be in 2 states, each spin can be in 2 states, I have 2 to the power 3 states. The generalization of this, if there are n spins, then there are 2 to the power n states. But then the question is, does all these states belong to the same macro state? If you look at it carefully, that this corresponds, let's define first the magnetization, which is sum over the spin values. Now Si can be plus minus 1. Just for our computational ease, we will take a value of plus minus 1. So this corresponds to a magnetization. This corresponds to a magnetization of m equal to 3. This corresponds to a magnetization of m equal to minus 3. And you see all these states corresponds to a magnetization of m equal to 1. And this corresponds to a magnetization of m equal to minus 1. So for our case, if I want to describe the system, particle number n, macroscopically I want to describe, which means within the scope of thermodynamics I want to describe this, particle number n, temperature and magnetization are the thermodynamic variables which are relevant. Not all these microstates belong to the same macrostate. These 3 microstates belong to the macrostate which has a magnetization of 1, and these 3 microstates belong to the macrostate where the magnetization is minus 1. Therefore, with these two systems, with these 2 examples, it's very clear that for a given, this is of course the case when I have 3 spins. You can see that if I have 2 to the power n spins, all the number of microstates for a given magnetization will also increase. We will do it when later on when we do statistical mechanics, we learn how to count such microstates. Now, so therefore, the whole idea is a macrostate always corresponds to infinite. Well, let's modify this thing a little bit for this case. It corresponds to a large number of microstates. In principle, it corresponds to an infinite number of microstates, because whenever you study these systems, you always say that n is very, very large, and we have seen that the typical value of n is 10 to the power 23. So therefore, we have the following idea on thermodynamics. That given a system, if I want to describe it using thermodynamics, using the framework of thermodynamics, I will define the state of a system, which is a macrostate, using macroscopic variables. Macroscopic variables which do not change with time. Again, I repeat that this is a very important property. In statistical mechanics, what we shall see is that fluctuations in these physical variables are very, very important, and we shall use these fluctuations. Now, what kind of question you can ask? You see, this in some sense that thermodynamics is limited, and therefore the kind of question and answers that you can get using thermodynamics is also limited. So one of the most important things that you can ask is, how does the response function behave? What is the response function? Response function is very, very simple. So given a system, I can perturb the system, which means I can apply a field to the system. How does the system behave? How does the system react? That is given by the response function. Take the example of a hydrostatic system. For a hydrostatic system, which is in a thermodynamic state, and is in equilibrium, we shall always deal with these systems. In thermodynamics, we shall always deal with systems which are in equilibrium. In principle, okay, we'll come to this later on. So the thermodynamic state, which is in equilibrium, right? So it is characterized by pressure, volume, temperature, and particle number. Now you compress the system a little bit. The little bit is important because the reason it's important is because you're staying in the linear response. So these things you learn slowly. So anyway, the idea is that we compress the system, which means that if I have this particular system, one part of the system is a piston, and I compress the piston, right? So that the gas is compressed. That's what you observe, that the volume decreases. How do you know that? That effect is given by the quantity del P del V. It's the other way around. So it is given by the quantity 1 by V del P, temperature constant, with a minus sign. I am holding the temperature of the system constant, that's why I have given the temperature constant. This is called the compressibility of the system. Right? Specific heats are also examples of response function. Specific heats, for example, CV, which is d cut Q, d cut T at constant pressure, and CV is d cut Q, d cut T at constant volume, are also response functions. So thermodynamics is well equipped to answer these questions. Right? For a magnetic system, you know that there is a magnetic susceptibility is there. Interesting to note over here is that there are two kinds of specific heats I have defined. One is at a constant pressure and the other one is at a constant volume. We are going to come back to these definitions, the more general definitions of this. Right. So now, given a macro state, which is characterized by a set of variables x1, x2, x3, so on and so forth. Right now we'll write it down in this particular way. You see, some of these variables are extensive in nature. What does extensive mean? That means they scale as particle number n. So if you add more number of particles, you will see that that particular physical variable also changes. For example, you can see that volume n for a hydrostatic system, volume and n. For a magnetic system, magnetization. All of these are extensive variables. So if you have a system which has n particles, if you double up the particle number, then n also doubles up, right? On the other hand, if you look at this for pressure and temperature, and in this case the magnetic field, they do not scale with particle number. So an extent, these are essentially, they do not scale with particle number, or the other way of saying is with system size. These are called intensive variables. And these which scale with particle number are called extensive variables. We want to make one more classification here. It is understood here that you see these quantities. Now just look at, for a let's start with the hydrostatic system, which is this one. Here of course there is yet another quantity which is called the chemical potential of the system, which probably you have encountered when you did chemical kinetics. Now here, for example, if you look at these thermodynamic variables that are given to you, two of these which are essentially extensive variables, volume and particle number, the other three which are intensive variables, not scale with number. You see, P dV, mu dN, if I want to look at these two, they have the dimension of energy. Similarly, for a magnetic system, B dm has the dimension of energy, right? And it's interesting, and this is where the analogy with mechanics comes. This is a force and this is a coordinate, a generalized force and a generalized coordinate. These are all forces and these are all coordinates which you can. Therefore, for a macroscopic variables, I can classify them in two categories. I have a set of generalized forces and I have a set of generalized coordinates. These are extensive in nature and these are intensive in nature. I can combine them to write down the work done as sum over Fi dxi. Right? So, given any arbitrary system, the first task is to identify the relevant macroscopic variables. And once you have identified these relevant macroscopic variables, you can easily figure out of these which of them are extensive and which of them are intensive, right? Moment you have identified which of them are extensive and which of them are intensive, you immediately understand. You immediately also take the next step in saying that these are my coordinates and these are my momentum. Sorry, my mistake. These are my forces, right? Let's take some examples. I know that for a hydrostatic system, pressure, for a hydrostatic system, my thermodynamic coordinates, which are extensive, are volume and particle number. So we will write extensive on top and intensive on top. Pressure, chemical potential, and temperature are the intensive variables. For a magnetic system, I have only the magnetization, and therefore the magnetic field and the temperature are the intensive variable. For a, let's say, film, for example, a soap film, right? You see the area is the extensive variable. Area of a film is the extensive variable, and the surface tension is the intensive variable. For a wire, metal wire or a rod, the length of this is the extensive variable. So if you keep on adding more and more rod, the length is also going to change. It's going to scale with particle number, and the force, the extensive force, is the intensive variable. So it's always important to note that given any arbitrary system, I can describe that system thermodynamically by identifying the relevant macroscopic variables. And once I have identified the relevant macroscopic variable, all I am left to do is to identify which of these are extensive and which of these are intensive variables. Once I have identified that, then I know that the work done is PdV plus mu dm. Here I want to write down as minus P, because the pressure that we measure for a hydrostatic system is the way we calculate it. Essentially, we calculate it by calculating the change in the momentum of particles which are hitting the wall. So when you calculate the pressure, this is the wall of the container. The particles come, they get reflected back like this way, and you calculate delta P, the change in momentum, is twice mu, right? We do it this way. By Newton's third law, the wall also exerts an equal amount of force, which is negative in sign. Therefore, by our sign convention, the pressure is negative over here. For a magnetic system, I have B dm. For a soap film, I have sigma dA. The temperature is also here, the temperature is also here, and I have F dl. Throughout this course, the sign convention for the energy is the following. Energy added to the system is positive. Energy taken away from the system is negative. Please understand that. I mean, you can follow any sign convention, that is okay. For me, right now, for all the set of lectures that we are going to give, the energy added to the system is positive, the energy taken away from the system is negative. We shall use this later on when we start to write second law, first law. Right. So this is what we have. This is fine. So now that we have understood that how to write down, how to identify the relevant thermodynamic variables given in an arbitrary system. But then where do we go from here? every thermodynamic, so let's not write down like this way, let's say that there are three sacred laws. Well, actually there are four of them. There are three laws in thermodynamics. Which you have done. The zeroth law, the first law, and the second law. Right? This is the guiding principle of thermodynamics. The zeroth law is very, very interesting. Even though apparently it is very intuitive or very, how do you say it? So it's very intuitive, it's very clear, obvious. It brings in a very important tool. It brings in the concept of an empirical temperature. The first law, is just the conservation of energy. And the second law essentially introduces entropy to us. Right? So we shall revisit all these laws. So any thermodynamic process must obey this zeroth law, first law, and second law. The zeroth law is extremely significant in the sense that what we understand as temperature is introduced by the zeroth law. Now, given a thermodynamic system, of course, the system is never going to remain in its state. You have to, at some point of time, it's very natural that you take the system to a different thermodynamic state. Therefore, essentially, if you take a system from state A to state B, you have done a thermodynamic process. And thermodynamic processes are usually guided by the first law and the second law. This must dictate what kind of processes they are. In thermodynamics, not only that we say that A and B are equilibrium states, then only I can apply the concepts of thermodynamics. We also say the processes are typically reversible or quasi-static. The main consequence of this statement that these processes are reversible or they are quasi-static is essentially at every point while it undergoes while the system goes from state A to state B, thermodynamic variables are well defined.